There's any good news here? We are going to start a new chapter. It's chapter 12. And chapter 12 is called Graphing and Optimization. All right, graphing and optimization. So what we hopefully have put into our toolbox in the first couple of weeks of this class is the ability to take the derivative of functions, right? And now what we're going to do is see how we can use the derivative to help us achieve this thing called optimization. And I alluded to this in the beginning of the semester as to what it is we're trying to do. And it's going to take us like baby steps to build up to this, but our ultimate goal is going to be able to take a look at a function and try and figure out, where these highest and lowest points are on the graph. Because in terms of like a business model, these points would be important. And ultimately, we would want to know where that highest point is. Maybe if this is a profit function, we want to know, like, when were we achieving the highest profit? Or, hey, look, when did this happen, right? Oh, that's when we hired Joe, and, Joe's a slacker, and look at production's down, and, we analyze the data, but we want to find the peaks and valleys of this function. And to do that, we will need the derivative. But to start, we're going to talk about, in 12.1, how the first derivative, taking the derivative, right, how that helps us with the graph and how it's connected to graphs. So the first derivative and graphs. Now, when I say first derivatives, that means we take the derivative one time. That's all we've ever done, right? If I've given you a function, I've asked you to take the derivative, right? You took the derivative, found f prime of x. That's called the first derivative. If you take that answer and take the derivative again, that's called the second derivative. And if you take that answer and take derivative again, that's called the third derivative. We haven't talked about those yet. They will play a role, but this first section talks about first derivative. So I want you to understand, we're talking about the derivative we've been doing this whole time. It's just the first derivative. So how is that connected to a graph? So what I'm going to do is draw a picture here for you. And let's just take a function that goes like this. It's going to go up, and then it's going to come back down like that. And we have a highest point on this graph, and let's bring this down. And let's just call this point A. This is the function f, all right? So this is the graph of f. What I'd like for us to discuss is the derivative of this function. Not the function, but its derivative. So tell me, if I pick a point over here to the left of A, somewhere between 0 and A, if I pick any point and I go up here, is the derivative going to be positive or negative or 0? Positive, why? Because the slope of, we know that the tangent line would look like that, right? And remember with lines, this is very important, when you look at a line, the slope of this line is 0, right? The slope of any line that goes like that is positive, and the slope of a line that goes like this is negative. So as long as I'm to the left of A, if I pick any point over here, do you agree that the slope of the tangent line at any of these points would be positive? Yes? So what I'm going to do is just below this, I'm going to draw a little dotted line, and I'm going to put over here f prime of x would be greater than 0, and that means positive, right? So anywhere to the left of A, my first derivative, my derivative is greater than 0. Agreed? As long as this x is somewhere between here and here. Now once I get on this side, what happens? Any point over here, you go in, you look at the function, you take the slope, slope of the tangent line, bless you, is going to be negative, right? So here my derivative is less than 0. Does anybody have a question on that? Sure? That's pretty straightforward? Okay. What we're going to want to do is kind of the reverse of this. I'm going to give us a function, like f of x equals something, and then we are going to try and determine where this is happening. Like, where is the function doing this? All right? Before we do that, I need to give you some definitions, and then we'll talk about them and see if they make sense to you. All right, so first definition here. A function f is said to be increasing. That's the word I'm defining, increasing, on an interval I if f prime of x is greater than 0 on I. So let's go back to the picture. If we look at this picture and we read the picture like we would a book from left to right, if we were actually standing physically on this hill and we started to move to the right, we would actually start going up, wouldn't we? We'd be increasing until we get to the top, and then once we get to the top, we would be going down. So this is saying that a function will be increasing on some interval. Here the interval is between 0 and a. That's our interval. We're increasing here because our derivative is positive here. So as long as your derivative is positive, we will be going up. And then decreasing would be the opposite of this, right? It would be a function f is said to be decreasing on an interval I if the derivative is negative on I, less than 0. So we'll do that one below. Function f is said to be decreasing on I if f prime of x is less than 0 on I. All right, let's do an example. So as an example, let's look at the function f of x equals x squared minus 5x plus 4. That's your standard old quadratic function, isn't it? I would like for us to find the following. Find where f is increasing and decreasing. So that means I need to figure out anywhere that this function is going up and anywhere where this function is going down. Right? So to do this, I need to figure out where the derivative is positive and where the derivative is negative, right? So there's a standard kind of approach to this. What we're going to do is we're not going to actually go and look immediately to figure out where it's positive and where it's negative. We're first going to figure out where it's 0. Now, let's try and understand that. If I tell you that something goes from a positive number to a negative number, doesn't that mean it must go through 0? Like if you have positive numbers and then all of a sudden it becomes negative, it had to go through 0 for that to happen, right? So what I'm going to do to start this is first determine where that derivative is 0. So that's my first step. So here's my solution to this. First step, I need to set f prime of x equal to 0. Okay, that's going to be the first thing I do. So we need to be able to take the derivative, don't we? And what is the derivative of this function? 2x. Keep going. Minus 5. And that's it, right? That's our derivative. So if this is still trouble to you, and on the test, you all did pretty well on this part, on the power rule and the product and quotient, you all did decent on it, and chain rule wasn't bad. So this derivative right here is 2x minus 5, and now this is what's new. We need to set this equal to 0. So we need to actually generate this equation and then solve it. And this is just a nice little linear equation, right? You could solve this for x. So I would just move the 5 over, and that means add 5 to both sides, and then I'd divide by 2. So I get 5 halves. Is this okay? Now, all this is telling me is that the derivative is 0 at this x value, right? It's 0, and that's not what we're interested in. We're interested in knowing where the derivative is positive and negative, right? So now what I'm going to do, this is step 2, is I'm going to plot the solution from part 1 on a number line. And split into regions. Now let me explain this. I'm actually giving you, right here, I'm actually giving you the set of steps we're going to follow. The first thing we do when we're trying to figure out where a function is going up and down is we set the derivative equal to 0. The second step is to plot the solutions on a number line and split the interval into regions. So let's take a look at this step 2, because in words it may not make a lot of sense. So I'm going to take a number line and I'm going to plot the solution I just got onto that number line. And my solution was what? 5 halves, which is, 2.5, but I'm just going to draw a number line and I'm going to put 5 halves here. Right? There it is. I'm going to plot that solution on a number line and then split into regions. What I mean by that is I'm going to use this 5 halves as a way to split my number line, and notice that since I only had one answer, it splits it naturally into 2 different regions, doesn't it? If I had 2 answers, it would split it into 3 regions. But we'll get to that as we move ahead. We good? That's step 2. Step 3 is to, I'll do it right here. 3 is to pick any test point in each region and plug it into f prime. So let me try and again explain what we're thinking here, okay? The thought is this. We ultimately want to know where the function is going up and down, right? What we've determined is that the slope of the tangent line here at 5 halves is flat, right? It's flat, it's 0. The slope is 0. So if the slope is 0 there, then that means to the left of it, I'm either positive or negative, and to the right of it, I'm either positive or negative. I don't know which one it is, right? So I'm going to pick some point over here, any point that I want. And I'm going to take that point and plug it into the derivative and see if it spits out a positive or a negative number. I'm actually testing to see what's happening. And then I pick a point over here and do the same thing. I have to pick one in each region. So you get to pick any point you want over here. So what would you like me to pick? Just has to be a point that's to the left of 5 halves. Half would work, 1 would work, right? Any of those would work? How about 0? Isn't 0 always a really nice number to plug into anything? Let's use 0 because it's clean. So I'm going to pick 0. I'm going to circle it because that's my test point. What's a point that I could test over here? Be careful. Make sure you're to the right of 5/2. 3 would work. If you want to be real safe, you could go 10. It doesn't matter. You just need to pick something to the right. So you need to know that this is 2.5. So anything over here, I heard 3 first. 3 will work. I'm going to circle that. So I have 2 test points, right? Those test points get plugged into what? In for x, but into what though? The derivative. Not into f, because look, if we plug these points into f, it's just going to tell you where you are. That's not what I want to know. What I want to know is what's the derivative doing there? Is it positive or negative? So let's try and plug those in. And remember, here's my derivative, right? I'll write it down up here again. My derivative, just to have it ready to go here, was 2x minus 5. So now I'm doing step 3. Which is to plug these in, right? Plug them in. So what I need to do is f prime of 0 and f prime of 3. And I need to figure out what my answers are. So what is f prime of 0? Negative 5. Just plugging 0 in right there. And then what happens if you plug in 3? You get 1. So let's interpret this now. What does this mean? What is it telling me? Okay, so I'm looking at this negative 5, and what I realize is that number is less than 0, right? And this number is bigger than 0. So if my derivative is less than 0 over here at 0, that means my function is doing what over there? If the derivative is going, if it's negative, it's going down, right? So my function is going down over here, right? So what I'm going to do is this. I'm going to write down the derivative over here is negative. And that goes for any number I plug in here. I only have to test 1 point. But this would hold. If you pick any other points, it will still be negative. It'll be a different negative number, but it'll be negative. Okay, so the derivative is negative over here. What is the derivative over here? It's positive. The derivative over here is positive. That means if the derivative is negative, that means the original function is going down, right? So how am I going to say that? Well, I'm going to use a little arrow like that to mean the original function's going down. And over here, the derivative being positive means the original function is going up. If your derivative is negative, the original function is decreasing. If your derivative is positive, your original function is increasing. That means it's going to look something like this, isn't it? It's a parabola. We knew that to begin, didn't we? Like this was a parabola. It opens like this. Like we knew that already, that it was going to go down then up. But this is the actual mathematics behind it. All right? Now, we're not graphing it. We're just finding where it's going up and down. So let's answer the question, because we have not answered the question. The question was, find where the function is going up and down, right? Yes? So I'm going to answer. F is increasing on what interval? And then F is decreasing on what interval? So let's talk about where is it going up? Over here, right? How do we say that? Everything to the right of 5/2. How do we say that in interval notation?
X is greater than 5/2.
You could say x is greater than 5/2, but in interval notation, wouldn't we do this? 5/2, comma, infinity. Doesn't that mean everything from 5/2 on? Yes? How would we say where it's negative? So negative, the derivative is negative, is over here. It's to the left of 5/2. So everything over there all the way up to 5/2, we write that how? Negative infinity to 5/2. And that's it. We've answered the question. This is what I'd be looking for right there. All right, let's try something else. How about this one? Next example, f of x equals 1 plus x cubed. Same questions, same exact questions. Where is this going up and where is it going down? So my questions are find where f is increasing and where f is decreasing. Is it okay if I use those arrows instead of writing increasing and decreasing? Okay, the book is going to put the words increasing and decreasing. All right, so what's your first step? Find the derivative, set it equal to 0, right? Let's just write the derivative down up here because we're going to need it. What's the derivative of this function? Just 3x squared, okay? Right? All right, now, first step is to take the derivative and set it equal to 0, which means we set 3x squared equal to 0. Are there any solutions to that equation? Or how do you solve that? Divide both sides by 3. So that goes away. We get x squared is 0 divided by 3 is still 0, right? What's the only number you can square and get 0? 0, right? 0 squared. Now you could do the square root on both sides right now, but you're still going to get 0. So the only solution to this is 0. Now what? Put it on a number line. Put it on a number line. That naturally splits this up into 2 regions, doesn't it? Then what? Take 2 test points here. So what would you like over here? -1's a nice one. Over here? 1. Notice when I'm doing this, that when I do my test points, I put little X's here. I don't put dots. I suggest you do little X's because of what's coming later. We will be plotting things later. We don't want to confuse these with points on our graph. So I circle it because it's a test point, and I put little X's because it's a test point. And now my third step is to plug those in, right? Or wait, yeah, the third was to plug in test points. So what am I going to be plugging in? I'm going to be doing, those go into the original function? Derivative? What are they? Derivative, right? So this is f, I need to do f prime of -1, and I need to do f prime of +1. And this is my derivative right there, right? So what happens when I plug -1 in there? I get +1 because I square it, and that just gives me 3, doesn't it? And if I plug in +1 into that and square it, I also get 3, don't I? So I get positive in both cases. They're both greater than 0, right? Which means to the left over here, my derivative is greater than 0. Over here to the right, my derivative was greater than 0. And that means my original function is doing what over here? What's my original function doing here? It's increasing, right? And then over here, it's still increasing. Okay. That means it did not go up and down, right? This one's up and still up. So now I need to figure out whether or not I have an interval, like what my interval would be. Do I have 2 intervals? Or is it just one interval? Because it looks like f is, if I'm asking where is it increasing, isn't it like always increasing and then it just keeps increasing? Yes? So we could say it's like everywhere, right? Everywhere? Negative infinity to infinity? Here's the one thing you have to be careful with though. Just check. Remember, something important is happening at 0. Something has to be happening. Because my derivative is 0 there, right? So something is happening here. Can we plug 0 into the original function? Can you plug this number right here into here and get an answer? Yes. Okay? That means that this number is in the domain of the function. That it's allowed. So that means I can say that my function is increasing like from negative infinity all the way through. See, if this 0 couldn't get plugged in here, then we would have a problem. I'm going to show you in the next example what I mean by that. But because that 0 can go in here without any issues, my answer to this part, where it's increasing, is negative infinity to infinity. Okay, that's my answer to this part. And then where is it decreasing? Never, right? Nowhere. It's not ever decreasing. And how do we say never in mathematics? We use the empty set. This right here is the set of nothing, which means it doesn't happen. Empty set, all real numbers, basically. Questions on that? Let me show you what this graph looks like, just so you have an idea in your mind of what it looks like. What is the value of this function at 0? If I plug 0 into this function, what do I get? 1. So at 0, I'm at 1, right? This is what this function looks like. Now let's just look at the derivative. If I'm moving from left to right, if I pick some point here, I'm going to have a positive slope, right? And I still have positive slope, still have positive slope. And then what happens right here? Just for a split second, it flattens out to 0. And that's what was happening right here. At 0, my derivative was 0, right? But as soon as I go past this point, what happens? I keep going up, right? I'm increasing. The slope of the tangent line is still positive. Are y'all satisfied with these answers? Does it make sense visually? Okay, let's try something that doesn't behave this way. Let's try something that's a little more complicated. How about x to the 4th plus 2x cubed plus 5. This is no longer a quadratic function, right? This is not quadratic, so we can't treat it like we normally treat quadratics. But we can follow the same procedures. We want to find where f is increasing and where f is decreasing. First step, take the derivative and set it equal to 0, right? Now again, I'm going to just find the derivative up here just so I have it. What is the derivative of that function? 4x cubed plus 6x squared. Good. That's your derivative. So the first step is to set that equal to 0. So I'm setting the derivative equal to 0, which means I'm setting 4x cubed plus 6x squared equal to 0. And we have to solve this. How do we solve this?
We get rid of the 4 and the 6 because you're dividing them by 0, so you're gonna get rid of them, right?
I can't get rid of both the 4 and the 6 at the same time. I can factor out a common factor from 4 and 6. Like I could pull a 2 out, couldn't I?
Yeah.
What else could I pull out? An x squared. So what we're going to do is we're going to try and factor the left-hand side. We're going to use greatest common factor. So I'm going to pull a 2 and an x squared out of the left. And when I do that, I have 2x squared, and I'm left with 2x plus 3 equals 0. So that step right there is just factoring, right? Now the whole point of factoring is so that you can set each of these factors equal to 0. So I can now set 2x squared equals 0. In a separate equation, I can do 2x plus 3 equals 0. Now what is the only number that I can do here that will make this work? 0, right? X is 0 is the only solution here. And what is the only solution I get here? I'd have to move things around, right? Like move the 3 over, divide by 2. So negative 3 halves. For the first time, I have 2 answers, right? Well, how does that change step 2? Number line. I've got more than one point now to put here. And I've got to make sure that I put them in the right order. So I've got a negative number and I've got 0. So I'm going to put the negative number first. Negative 3 halves. And my other number is 0. And this naturally partitions up our number line into 3 different regions, doesn't it? I have a natural breakup of 3 different regions. So now I need to pick my test points. How many test points am I going to need? I'm going to need 3. 1 inside each of those regions. So you need to give me some test points. 1, positive 1?
Yes.
Okay, that'll work. That's that one. Okay. Negative 2? Is that what I heard? Negative 2 would be over here, wouldn't it? And then you need something in there. Negative half would work. Negative 1 would work. I'm going to go with negative 1 because I want to avoid fractions. All right? So negative 1. And just remember, this number right here is negative 1.5. If you need to do that on your calculator, that way you know negative 1 is in here. Notice I don't even care about the spacing of these numbers. I'm just trying to get the order correct. Questions on that? Step 3. What am I going to do with those numbers? Plug them into the derivative. I need to figure out what's the derivative at negative 2. What's the derivative at negative 1? What's the derivative at 1? And that means we're using this function right here. That's what we're plugging into. And yes, you've got to figure out what that is, right? So you've got to do like 4 times negative 2 cubed plus 6 times negative 2 squared. Maybe I should have given myself a little more room here. So when we do this, when we do negative 2 cubed, we get negative 8. And negative 8 times 4 is negative 32. Then we have negative 2 squared, which is 4, then times 6, so 24. And so that gives me negative 8. All I cared about, though, was that this was negative, right? So this is less than 0. I mean, yes, that's less than 0, so that's negative. Right now, what I can tell you is that my original function is doing what over here? Decreasing, right? My original function is decreasing there. Now let's plug in -1. So 4 times -1 cubed plus 6 times -1 squared. What's -1 cubed? -1, then times 4? -4, okay? And then -1 squared is +1, and then times 6 gives me 6, and -4 plus 6 is 2, which is a positive number, which means that my original function is increasing when I'm at -1, right? In this little region, it's going up. And then finally, you plug in 1, and when you plug in 1, you should get 4 plus 6, which is 10, which is a positive number, which means what? It's still increasing. If you start thinking of this in terms of the business aspect, if you have a profit function or a cost function, you could start asking the question like, you know, when is your profit increasing? That's what we're basically doing here. We're saying when is the function increasing, but you could change that function to a profit function. So hey, when is our profit going up? When is our profit going down, right? So that's it. Let's try and figure out what the answer is in terms of the interval, because we need to answer the question from the very beginning. So where is the function going up? Let's start with that. Where's the function going up? So f is going up from, looks like here, right? Is where it starts. Now don't say from -1, okay? It's from your point that you got from solving that equation on part 1. It's from here, and it keeps going, right? Now what about at 0? I need to check something at 0 real quick. Can 0 go into the original function without any problems? Yes. So that means we can just use the whole thing from -3/2 forever. Right? So we're going to say that. This is increasing on the interval -3/2 to infinity. Now, where is f decreasing? So all the way coming this way. So -infinity all the way up to 3/2. Did I not put negative? Oh, I did not put negative. Thank you. All right, I want to try one more.
Or I have a question.
Yes.
So, like, does that mean like at 0 it flattens out at 5?
Right here
Yeah.
at 0,
Like, remember how in the last one we did?
like it did
was
like
how
that?
It flattens out?
That's a great question. The question is, at 0, is it doing that same thing like this? Most likely, yes, but actually to answer that question, we actually have to look at the second derivative, which we haven't talked about yet. But we will, and we will, later on, we will call this point right here where it does that little thing, we call that an inflection point. And in business, we call it the point of diminishing returns, but that's, again, we're getting ahead of ourselves. But notice on this graph that if you look at, you know, everyone knows what a smiley face looks like, right? And everyone knows what a frowny face looks like. I'll do it like this. Okay? All right? So like notice that on this graph, you're increasing, right? You're increasing, but doesn't, from this point on the left side, doesn't that look like part of a frown? Right? It doesn't look like any part of a smile, does it? And then on the right side, notice that that right side looks like a smile, part of a smile? Yes? So later on, the second derivative will tell us that whether or not we're frowning or smiling. And anytime we go from a frown to a smile, we have this inflection point. So I can't answer your question unless we can do that. It does do it though.
Okay.
It does. That's exactly what's happening there. But we're peeking into the future there. All right, I want to do one more. We have 10 minutes. So far, the functions that we've looked at have been pretty easy to take the derivative of. Would you agree? And relatively easy to set equal to 0. Okay, so there's our function now. Same question. Where is this function going up? Where is it going down? Where is f increasing and where is f decreasing? Well, we need the derivative, don't we? And to do this derivative, I'm going to need a little more time. So let me go ahead and just do the derivative right here. And what am I going to be using to do this derivative? The quotient rule. The quotient rule. Has everyone picked up their exams? I'm going to take attendance based on this exam, on who does not. Whoever did not pick theirs up will be counted absent. So, all right, quotient rule. Go ahead, work it out. See if you can get your quotient rule on that. Hopefully you're able to arrive at that derivative. You're doing derivative of the top one, right? Times the bottom, minus the derivative of the bottom one, times the top, all over the bottom squared. Is that fair? Question? See some looks of, you all right? I'm using the formula for quotient rule that we did that said that we have, remember that formula?
Yeah, I was confused on the order of the formula.
So it's derivative of the top function first. The derivative of this is just 1, because the derivative of x is 1, derivative of 4 is 0. Then times the bottom, which is your g. Then minus the derivative of the bottom, which again is just 1, because derivative of x is 1. Derivative of negative 2 is 0. And then times the f, which is the top function, then all over the bottom squared. And then you have to distribute or get rid of the parentheses, and just be careful putting that negative through here. So are we okay with that? Yes? Okay. Okay, that's our derivative. Step 1. Set the derivative equal to 0, right? And we're going to run into a problem. This is the first time we've run into this problem. How do you solve that? That seems strange. Well, I have some news for you that you should make a note of. A fraction can only be 0 if the numerator is 0. This is a fact about fractions. The only way that a fraction can ever be 0 is if the top is 0. So we have a fraction, right? And I would like to know when it's 0. And I've just told you that the only way that this can ever be 0 is if the top is 0, right? Yes? So this means that -6 would have to be 0, but that's impossible, right? Which means that there's no place that the derivative is 0. This function never flattens out. It doesn't have any point on it ever that you have a flat tangent line, because there is no solution to this. Does that make sense? You sure? Okay, so I'm supposed to draw a number line and put that point there, right? But I don't have a point to put. What do I do? Well, if you ever get to this point where you don't have a solution here and you go to part 2 and you draw your number line, you're sitting there going like, what the hell am I going to use for a point? What you have to do is this. Go back to the original function and just see if there's any points on the function that you have a domain problem, an issue with the domain. Is there anything here that we cannot plug into our function? Are there any numbers, values of x that we can't plug in? +2. You cannot plug 2 into this. Why? You get division by 0. So if there's going to be anything ever happening bad on this function, it's going to be at 2. And so because I have no answers here, I'm going to put that point here. 2. All right? So 2 is not in domain of the function f. And that will split up my number line. Now, if you look back at the previous problems that we had, did we ever have that? Like if you look back at all the problems I gave us before, the functions, they were all nice polynomials. You never had a problem where you would ever get division by 0, so you didn't have to worry about this. This example is to show you how things can start to get a little more complicated. All right, so we pick some test points. What do you say we go with 0? And how about 3? Yes? And where are these being plugged in? Into the derivative still. Because I don't know, am I increasing or decreasing here? I'm not sure. I know I'm never flat, right? I'm never flat, but I could be increasing or decreasing. So what happens when you plug 0 into the derivative? That's the third step. What happens when you plug in 0? So step 3, I need f prime of 0, and then I need f prime of 3. So what do you get when you plug 0 into, I erased the derivative, but it's this piece right here, isn't it? What happens when you plug in 0 here? You get -6 over 0 minus 2 squared, which is -6 over 4, which is a negative number, isn't it? It's a negative number. That means my original function over here is going down. What happens when you plug 3 in? You get negative 6 over what? So 3 minus 2 is 1, right? So 1 squared is 1. So you get negative 6 over 1, which is still negative, isn't it? Negative 6 over 1 is still negative. So my function's still going down. Like that. Okay. So let's try and answer this question. Where's the function going up? Never. So I use the empty set for that, right? The function is never going up. Here's the tricky part. Be real careful here. Where's the function going down? Everywhere? This is the tricky part. You can't say everywhere. Why can't you say everywhere? Because 2 can't be plugged into this function, right? So you can't tell me the function's going down at 2 when the function isn't even defined at 2, right? So you remember how I said take this point and just plug it in here and make sure it works? Well, it doesn't work this time. So that means that it's to the left of 2, which would be negative infinity up to 2, right? And then everything to the right of 2, which I'd put 2 to infinity like that. And then what symbol do we use in the between 2 intervals? The union symbol. That's a little more involved, right? So here's what I'd like for you to do for homework. I have not made the videos for these yet. Don't know if I'll get to them today. For sure, I would get to them tomorrow. But for the homework, follow the schedule. The good news is there won't be any problems like this on the homework, this one. I want you to do the problems that are assigned, which are 37, 39, this is page 644. 37, 39, 41, 55, 57, 59, 61, don't do that right now, okay? We'll skip that. But on those problems, it asks you to do a lot of different things that we haven't discussed yet. All I want you to do for these is what we did today. Just figure out where these functions are increasing and decreasing, all right? So if the instructions say something like, find the local extreme values, or to sketch the function, ignore that. Just do what we did today on these, all right? All right, that's it. I guess have a good weekend.